second lecture. So, topology. We need to do analysis of functions of complex variables. For this reason, we need to know the things concerning the properties of convergence of complex numbers. That's easy. So let Zm be a sequence of complex numbers. What does it mean that it converges? We say, as usual, we say this is simply the convergence of couples in R2. That is, we say that this sequence converges to a complex number A, which is the limit of our sequence, if for every epsilon positive there exists a number capital N which depends on epsilon, such that for every number n small, which is bigger than capital N, the distance between the n and A is smaller than epsilon. So this means geometrically that if you consider the point A on the plane, and if you consider any disk of radius epsilon centered at A, then there exists some number n dependent on the chosen radius, such that all points the n plus 1, the n plus 2 are contained in this disk. If you consider the smaller radius, you shrink your disk, then you can increase capital N, but after this, for all n bigger than capital N, all points of your sequence are inside this disk. This means that your sequence Zn is convergent. If you write Zn at its algebraic form, then it's obvious from this definition that the limit of Zn is equal to A. Let me write A in the form alpha plus E beta in its algebraic form. So this is simply equivalent to the fact that the limit of the real parts is the real part of A, that is alpha, and the limit of imaginary parts when n tends to infinity is equal to beta, that is the imaginary part of A. All right, and as a consequence from this definition, all usual algebraic properties of limits of sequence remain true when you consider sequences of complex numbers. So if you have two convergent sequences, the sum converges to the sum of limits, the product converges to the product of limits, and so on. What we need, and it is crucially important for our course, we need the notion of the series of complex numbers. So if we have a series Zn, the series is convergent, and we have some S. Of course, the definition is absolutely the same as in the real analysis. This is the limit of the sequence of partial sums S capital N when capital N tends to infinity, and S capital N is a partial sum Z small z01 plus da 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 plus Z capital N, Z capital N, and if this sequence Sn is convergent in the sense of this definition, which we just have discussed, then this limit is called the sum of the series and the series called Convergence. I mean here that S, of course, is in C, right? S is in C. All right, so this is about the convergence, and that's essentially what we need. But we also need some additional geometric information about the complex plane, because this is a plane. This is geometrically much more complicated subject than the real line, right? So, next topic is the curves in C, and we need the curves because we need, you will see a little bit later, this is a fundamental object for us because the curves are indispensable for integration on the complex plane. So, curves in C, so consider a map phi from the interval alpha beta in R and with values in C, right? So this means that phi associates to every real t a complex number phi of. You can view this as a complex number z which depends on t. So that is, you can view it as x of t plus I y of t, right? So we always such a map is called the curve. It is continuous. So phi is continuous. What does it mean? Continuous at point t0 from alpha beta. This means that for every positive epsilon there exists delta positive such that the inequality t absolute value t negative t0 is smaller than delta implies that phi of t negative phi of t0 is smaller than epsilon. All right? So phi is continuous, phi is continuous if it is continuous at every point t0. So such a map phi is called a real parametrized in C. So I would like to stress the meaning of the word parametrized. Parametrized means that in our terminology a curve is not a geometric set of points of the plane. The curve is a map from interval to C, and the image of this map is a geometric set of points. So let us consider example, of course, which will be fundamentally important for our course. So the circle, if we consider the map phi from the interval z to p to c, and you set phi of t is equal to a plus r exponential it. So this is your z of t, right? But then you see that z of t negative a, just put a on the right side and take the modulus, is equal to r for any t. So this means that all our points belong to the circle centered at point A and of the radius r. So this is your r exponential it. And when phi, and what is very important, when phi rounds our interval z from 0 to pi, your point moves on the circle on this direction. On this direction, our disk remains on the left side when we move in this direction along our circle. So this means that our curve is not just a curve. Our curve is oriented. When you have a parametrized curve, you have a natural orientation, that is the direction in which your point runs over your curve when the parameter runs over your interval from the left end to the right end. In our case, from 0 to pi, and the point runs over in this direction. So this is the orientation of this curve, that is the direction in which the point moves, which is compatible with your parameterization. If you change parameterization, for example, you put here negative it, then you change orientation. Orientation will change. All right, this is very important. So in fact, the continuous curves are not very convenient for our goals, and we will never work with just continuous work. We will consider more strong assumptions on the curves. We will always suppose that our curve phi is of class C1 on the interval alpha beta. In this case, we say we are speaking about curves of class C1, or at least piecewise C1. This means that you have a partition of your interval alpha beta on finite set of intervals, and the restriction of the mapping phi on each interval is of class C1 on this closed interval, but maybe the derivatives, left derivatives and right derivatives in the points of partitions are not the same. So roughly speaking, you can have something like this. So so the left derivatives and the right derivatives exist at every point of the partition, but maybe they are not equal, so maybe there are no derivatives at this finite set of points. But this is not a big problem. The curves like this appears very naturally. For example, if you consider boundary of rectangle on the complex plane, the boundary of rectangle, it will not be of class C1, but it will be because of the points in the corners. There are no tangent line, right? Obviously, but of course this curve is C1, piecewise C1, in the sense of this definition, right? So if you have this type of curve of this class, you can take an integral over this curve phi from alpha beta to c, a curve which is which is piecewise C1, and so this means phi to every point t of your interval associates z of t, right, which is x of t plus I y of t, and then you can consider the integral over your curve phi, over your curve of your, you can consider the integral of phi of t dt over alpha beta, which is integral from alpha to beta of x of t dt plus I integral from alpha to beta of y of t dt. You can also consider the length phi, which will be equal to the integral from alpha to beta of the square root of x prime t squared plus y prime t squared dt. You know it very well from your course of the classical real analysis. Okay, so the next fundamental object which we need to introduce is the notion of a domain in Cn. Domain. So a subset omega in C is called a domain if it satisfies two properties. Omega is open, of course non-empty. This means that for every point A of omega, there exists R positive, maybe very small, such that the disk centered at point A and of radius R is contained in omega. So this means that you have something like this, right? And if this is your domain omega, then if you pick up any point A in omega, then maybe very small disk centered, very small disk centered at A is contained completely in omega. So this means omega is open. And the second omega is connected set. This means the following thing: for every 2 points A and B in omega, there exists a curve, we'll say gamma, which is contained in omega, such that the ends of these curves are the points A and B. So this means gamma from alpha is equal to A and gamma from beta is equal to B. So geometrically speaking, you have A, you have B, and there is a curve, gamma, joining A and B. And this curve is completely in your domain. So roughly speaking, what does it mean connected? If you consider two disjoint disks, their union is not a domain because the union is open, but it's not connected, because if you take here A, you take here B, you cannot join them by a continuous curve, right? There is a piece of this curve which will be out omega. So this is not a domain. So this situation is prohibited by condition 2 of the connectedness of domain. All right. Now we enter to the principal chapter, functions of complex variable. So let E be a subset of C, and let F be a function defined on E and with values in C. Such a function is called F is a complex function. So then we say that F is continuous at point A of E if the limit of f of z when z tends to A, remaining on E, of course, is equal to f of A. That is, what does it mean? This means that for every epsilon positive, there exists delta, which in general allowed to be dependent, on epsilon, so which is strictly positive, such that for every z in E, the condition z negative a modulus is smaller than delta necessarily implies that f of z negative f of a, this modulus, is smaller than epsilon. So this means the continuity. So of course you can write function f using its real imaginary part, right? So f of z is a complex number, so you can write its real part, which is a function of xy. Xy is a real and imaginary part of z, plus I v of x y. Then the continuity of f is equivalent to the fact that f is continuous at a if and only if u and v are continuous at a as functions of two variables, two real variables. Okay, so it's easier. Well, so there are a lot of examples, of course. Let us consider some examples. So function f of z is equal z power n, right? For any n which is integer, this is a function of complex variable. If you consider the real part of z, this is a function of complex variable. Z negative 2 times z bar, this is a function of complex variable, and so on, so on. Of course, there is a huge number of functions. So now we have to discuss sequences and series of functions of complex variable. This is important object for us. All right, so now sequences and sequences and series of functions. So this is very close to the classical theory. So a sequence of functions fn of z converges to the function f of z when n tends to infinity uniformly. This is very important, on a subset E of C if for every positive epsilon there exists an n integer which depends in general on epsilon, such that for all points z on E and all n bigger than n, we have the modulus fn of z negative f of z is strictly smaller than epsilon. This is the uniform convergence. Of course, this is the same thing as to say that for every n bigger than n, the supremum z runs over E of f and of z negative f of z is smaller than epsilon, right? So you can see here, and of course there is the classical Weierstrass theorem. From the real analysis which says that if the functions f n are continuous, on E and Fn converges to F when n tends to infinity uniformly, on E, then F is continuous, So this is a very classical and important result of the real analysis. And another version of this theorem, which can be applied to the series of functions. So assume that for every n, the supremum of Fn of the modulus of Fn of z over E is smaller or equal than Cn, and the series Cn converges. Then the series of functions Fn of z converges uniformly on E. Converges uniformly on E. The proof is very simple and uses the Cauchy criterion for convergence, for uniform convergence of a series. So this is a classical result of the real analysis. This is still not complex analysis. Okay, the complex analysis, in fact, begins now. The analysis of functions of complex variables. It begins with the notion of the derivative. And now we enter to the main part of our course. Because until now it was a preliminary. So derivatives. So first of all, of course, as you know very well from the classical course of functions of real variable, the notion of derivative is closely related to the notion of linear mapping from the linear algebra. This is not completely clear in the classical situation of functions of one real variable, because in the classical courses of analysis, usually the derivative is identified with the differential, which is linear mapping, but linear mapping from R to R is uniquely determined by its matrix, which is just one number derivative. So usually people do not take care about this. But when you consider functions of two real variables, the linear algebra appears because the differential is the linear mapping, and the Jacobi matrix is its matrix in the canonical basis of R2 and R. So let us discuss first the notion of a linear mapping. Already this is not so easy. So first of all, there are two types of linear forms of functions. So R linear, I mean in C, when we are working on the complex plane. So R linear and C linear functions. Forms, so R linear forms. So a mapping, a map L from C to C is called R linear. If two following properties are satisfied, of course, the image of the sum of two vectors is equal to their sum. This cannot be changed. And this is the crucial. For every real scalar, lambda, real, I stress it, we have L of lambda z is equal to lambda L of z. No, of course, for any complex z. So the word R linear corresponds to this property. We ask this property that we can put the scalar lambda before the action of our form only for real scalars. And of course, now if we consider the parallel definition, so the form is C linear if the same property 1 holds, and instead of 2 we have this property in the stronger form. We required for any complex scalar lambda we have, and of course for any complex z we have L of lambda z is equal to lambda L of z. So this is complex linear forms. Well, what is the relation between these two notions? Of course, if this condition is stronger, because if this assumption holds for any complex lambda, in particular it holds for any real lambda, right? So C linear implies R linear. R linear. R linear. Now, let us describe the general form of R linear and C linear forms. R linear and C linear forms. Okay, so let us consider first C linear form. Okay, so C linear. What is the action of C linear function? So if we consider L of z, we can write it like L of z multiplied by 1, right? And because of our form is C linear, we can the number z before the action. So this is z times L1. L1 is just a complex number c, which is fixed, so we obtain az. Thus we obtain that the action of a complex linear form is extremely simple. This is L of z is equal to az for any z. So this is the general form of a complex linear function. This is the general form of a complex linear function on C. With real function, situation is more complicated. Suppose now that we have R linear function. So we have this L of z, right? So this means that we can represent z in its algebraic form, x plus iy, and then we use the first property of linear functions and we replace it by L of x plus L of iy. Now L of x, similarly as before, can be written as L of 1 multiplied by x. And here we use the fact that y is real, right? Y is real, and x too, and our form is real. So the factor y we can put before our form. So we can write L of I multiplied by r. So now if we denote L of 1 by A and L of I by B, well, let me denote it by alpha and beta. We obtain alpha x plus beta y. Now let us go back to the complex notation. So we can write z is equal x plus y iy, z bar is equal to x negative iy. If we take now the sum, we see that z plus z bar is equal to 2 times x. So we see that x is equal z plus z bar over 2, and if we consider the difference, we see that y is equal z negative z bar over 2i. And we substituted it instead of x and y. Sorry, I continue there. And I still continue my equality. I obtain alpha z plus z bar over 2 plus beta z negative z bar over 2i. And now we can rewrite it. Of course, we can rewrite it in the form 1 over 2 alpha negative I beta. Now here I use the fact that, so I will write it here, 1 over I is of course negative I, right? So z plus 1 over 2 alpha plus e beta z bar, right? And now I use the notation, this is A and this is B, and so we write A z plus B z bar. So let us sum up what is our conclusion. So we obtain that our linear function has the form L of z is equal az plus b bar, where a is equal 1 over 2 alpha beta, b is 1 over 2 alpha plus I beta, alpha is L of 1, and beta is L of I. And so if we compare this expression with the expression for a complex linear function, we see that L is C linear if and only if B is equal to 0. So this is the crucial condition which will appear everywhere through our course, and so this is the end of our second lecture. So see you soon.